All right, welcome. In this video, I'm going to continue talking about proofs of correctness for greedy algorithms. And I'm going to do that by looking at another problem, a little bit of a novel problem, a toy problem called library books. Before we do that, I do just want to talk a little bit about some of the properties that optimization problems have, because these properties show up a lot in our proofs of correctness, but also our proofs of correctness in greedy algorithms are typically for optimization problems. Not always, but typically. So first of all, what is an optimization problem? Let's just refresh our memory of that. Well, an optimization problem is one that tries to find an optimum, and what an optimum is just a minimum or a maximum something, and usually that's a minimum cost or a maximum reward for something. Okay, and so these are very common problems. And then usually when we're stating an optimization problem, these problems usually have two different characteristics or two different ways to characterize their outputs. One of the characterizations tell us what is a valid output, and another characterization tells us what it means for that valid output to be also optimal. So we call these the properties of validity and optimality, and I'll be a little bit more clear about what these are. So a solution then is going to be valid if it counts as an acceptable solution, though it might not be the best solution. And this is important because usually for problems, some outputs are going to be acceptable while others are not. Okay, a very common greedy algorithm used in everyday life is making change for a retail purchase. So maybe you give them a $20 bill and they have to figure out what $4.35 is in dollars and coins. And usually the optimal solution is we want to have the minimum number of bills and coins possible. And luckily, built into our monetary system, there is a greedy algorithm that is guaranteed to give us that minimum number of coins. But if we're making change, you've probably been at the 7-Eleven or something before where the clerk says, oh, I'm sorry, I don't have any quarters, but here's 10 dimes or something like that. We would accept that, but we might not be very happy about it. That's an acceptable solution. Whereas if they said at the counter, I don't have any quarters, too bad you don't get any change, we'd say, no, that's not an acceptable solution. You need to give me the change. Or vice versa. Maybe if they said something like, I don't have any quarters, but here's, a bag of potato chips or something, you might say that's not what I wanted either. Some of the solutions are valid and some are not. Okay, that's what we're getting at here. Now, the one where they actually give us the 4 quarters, the things that we need, or the $1 bill would be even better, would be the optimum. That's the optimal solution, is the one that also minimizes the coins that we use. And so optimal solutions are always valid, but valid solutions are not always optimal. And so usually, and then the other thing that's important is for our algorithms, they better return both valid and optimal solutions. We often focus on the optimality part, assuming that most people can verify that it does actually output a valid solution in all cases. But again, optimal solutions are valid, and so it's important when we're proving optimality to, at least in certain cases, be conscious of the potential that our solution might not be invalid. Specifically, when we start taking a solution and making changes to it, if it started out valid and we make a change to it, it might not be valid anymore. So we want to make sure that we only are talking about valid solutions. So I just wanted to jump back to that example from the last video, which was the job selection revisited problem, where we changed the criteria on what days you can work from, not day I and not day I plus 1 kind of thing, to you can only work K days. It doesn't matter which days they are. They can all be in a row. You can take off breaks in between them. It doesn't matter, but you can only work K of them. And we came up with a greedy algorithm and proved it correct in that last video. But in this one, I just want to see, can we use this problem statement to try and figure out what the properties or the characteristics of validity and optimality are for this job selection problem. Okay, so, and I'm just going to highlight what I think they are here. Okay, This whole business here where we've got, okay, A is a subset of 1 to n is a set of indices such that that set is of size k. What that's basically saying is for a solution to be valid, you have to pick jobs from the jobs that are provided. That's what this bit is saying. Only pick jobs from the ones that are provided. And then, this is the other important thing, there better be k jobs. Okay? If our algorithm returns k plus 1 jobs, that's invalid. That's not even an acceptable solution. If it returns k minus 1 jobs, again, invalid, not acceptable. If it returns k jobs, then it's valid. It might not be optimal because we haven't got to that bit yet, but it's valid. So any set of k jobs is acceptable. And so we could imagine bad algorithms for this that just return the first k jobs or something like that, but those would still be valid solutions. Not optimal, but valid. Okay. Where's the optimality come in? It's the extra bit here that we haven't been looking at this bit with M. Okay. M is the maximum possible payout. And if you added up all the ones in this set that we were talking about, they achieve that maximum. So that's sort of what I've got here. So our solution must be a subset of size k. That's the condition of validity. But it must have the maximum total payout is the condition of optimality. Okay, with those ideas or those definitions in mind, let's go and take a look at our new problem. Okay, so our new problem here, library books problem. I'm going to describe it in English first. Okay, so in order to get the best grade in your algorithms class, you've taken out n books from the library. Unfortunately, you didn't read any of them, and now they're all overdue. And you will be charged $1 per day per book. You have estimates of how long it's going to take you to read each of the books, and you've estimated that in days. And you have decided that what you're going to do is read the book one at a time, and then you're going to return it once you're done, so you don't have to keep accruing late fees on that one. And you want to know what order you should read the books in order to minimize the cost of the total overdue cost. So the first thing I've got here is, well, can we formalize this? And this is often a problem you have to do as someone working in industry. Your boss or your customer comes to you with this paragraph, and you need to produce the input and output criteria. So what is the input here? Well, we can start scanning here and see if we can pull things out. N seems to be part of it, but it's only part of it. It's the books that are really the input, not really the N. And what about the books is important? Is it their name, their subject matter? No, none of that stuff is really relevant to our problem solving here. What is important is this, how long it takes to read them in days. So what we really want our input to be is the length of time for each book that it will take us to read it in days. Okay, so that might be our input. Anything else coming in as input? Nothing I can see off the top of my head here, but that doesn't mean we're exhaustive. It just means, okay, it looks like we got the big one here, the books. Okay, sometimes when we get to the output, we go, oh wait, I forgot an input. Okay, so what do we need to say about the books? Well, let's try and see, what are they asking us to do? Maybe often the last sentence tells us what we want to do. So you want to determine the order. I want to highlight that, or I want this is where I'm underlying something. Okay, the order. What is an order? Like a permutation. Okay, I'm reaching into my mathematical definitions now and being like, what is the mathematical word for this? Oh, permutation. Okay, that means take that set of jobs and switch them around, but don't add any new ones in and don't leave any ones out and don't make copies of any of them or anything weird like that. Just mix them around, move them into a different order, and that's what our output is. So I'm expecting now in our output sentence, I want there to be the word permutation showing up somewhere there. Okay, why? Permutation brings in all that good mathematical definition with it, which is less vague than order. Okay, order kind of carries the same thing, but it's informal, and so your reader might think, do you mean permutation? And if you do, then you should say permutation. Okay, so what about that permutation? It's a permutation. So remember, we were just talking about validity and optimality. So what are the conditions here for validity and optimality? I think the order bit that we were talking about, that's the validity, right? As long as you tell me to read the books in some order, that's a valid solution. Is it the optimal solution? Is it going to minimize my costs every time? Maybe not. But is it Is it valid? Yes, as long as you give me an ordering, it's valid. Okay, well then that might ask us, well then what is the condition of validity, or sorry, of optimality? Well, we just hit it. It's to minimize the total overdue costs. And both of those properties need to show up in our output. Okay, somehow we need to formalize it in our output saying some permutation such that if we sum them in that permutation, we will get the appropriate overdue cost. Okay, and that's sort of what we got here. Let's see, we got the word permutation in there, it looks like. Okay, we've got the books for n books. N is not usually considered part of the input, rather it's just a property of this list that we've been given. Okay, but then also what do we want for our output? Notice how I've done this. I've assumed T is already a list in an order, so I'm going to call my output T prime, like it's a permutation of T. Mix them up. We might literally do that in the list. We might literally sort them or something like that. The order of the books, this is the order that we want to read them in. This permutation here is the order we should return them in so that we can achieve the minimum cost M, whatever that might be. Now you'll notice here, I've left something vague in this problem statement, which is not necessarily good. Okay, what I've left vague is the formula for calculating the cost of the total minimum or the total overdue cost for a particular order. And that's because that formula is maybe non-trivial and I want us to, work it out a little bit. Okay, so I guess we got spoilers here, but what are the conditions of validity and optimality? Well, we already highlighted this when we were trying to come up with our output there. Valid is it's got to read and return all the books in some order. That's the permutation criteria. And then optimality is minimizing the total overdue cost. All right, let's explore the problem a little bit more. Now, this is something that I think is important for us to do. Even if the obvious solution is jumping out and screaming at us already, saying, do it this way, do it this way. It's usually a good idea, just write down some inputs, figure it out, maybe even just test to make sure your algorithm works for those inputs. Proof by example is not the right way to do the proof, but there's nothing wrong with just grabbing an example and seeing if your algorithm works. Because if it doesn't work, it's not right? So, and if it does work, if your algorithm is indeed correct, any input you pick should work. So, it's not like you're crafting the input just so it works. You should be able to pick any one and it should work. So let's look at this one. Let's see. Now, I'm not even asking what the right output is yet. I'm just saying, what is the cost if we read the books in this order? Okay, so imagine we're just not even going to put any critical thinking into it. We're just going to read them in the order, like the pile that they're in, and maybe the one on the top is going to take us 5 days. Okay. Now the other thing we're going to notice is we have 1, 2, 3, 4, 5, 6 books here. So while we're reading this first book that takes us 5 days, it's going to cost us $6 each day. So I've kind of got this formula here, where the first day, or the first 5 days rather, we're going to have 6 books out, so we're going to read them. That's how much money that's going to cost us. Then the next book takes 2 days to read, but while we're reading it, there's only 5 books out, and so on. Then 4 books that's for 4 days, 3 books for 1 day, 2 books for 3 days, and then 1 book for 6 days. And if we add all these numbers up, and again, go and double check my math to make sure it's right, we end up it costing us $71. Okay, is that exciting or interesting to us? Probably not. Okay. These are the numbers 1, 2, 3, 4, 5, 6. If we put them in the order 1, 2, 3, 4, 5, 6, we get, 1, 2, 3, 4 is 10, 5 is 15, 6 is 21. So we can actually do this with $21, which is a considerably, actually, I just added all my numbers together. So that's not right. I didn't add in the 6 and the 5 and the 4 and the 3 and the 2 and 1. So I tried to do it all in my head to see what it would be. And my head is not a good enough calculator to figure out what it would be. But I'm guessing it's going to be less. Okay, and we could go ahead and test it yourself. I don't actually have it on the slides here what the other one is, but you could go and test it yourself. And sure, if we put them in the order 1, 2, 3, 4, 5, 6, we should get a lesser cost. Okay, less than 71. Now that wasn't the purpose of exploring this here. The purpose was because I want to know what the total overdue cost would be, not for this, but for an arbitrary input. I want to be able to write it down. Okay, now there's 2 things we'll notice in this. We've got a sum here. So if we're writing it down, the first thing we should write is a big summation sign, right? We've got a sum. And then a sum of what? Okay, well, one thing we've got here is this, the second term here are just these numbers here, the time. So for our permutation t prime, that would be t prime of I, say. Okay, so one of our terms is t prime of I. The other term is the one that I want us to put some thought into, is because it's counting down. If we started on the right hand side, it goes 1, 2, 3, 4, 5, 6. That's kind of easy for us to come up with, but it's not. It's counting down, because if it was going that way, it's just I, right? But if we're going back down, we start at n, which in this case is 6, and we end at 1, which is the bottom. So to get it to do that, we actually need a slightly different formula. Hopefully our instinct is already saying maybe it's something like n minus I, and that would be indeed right if that's your instinct, except it's n minus I. We need to do a +1 on there to make sure that we get our index instead of going to 0 to n minus 1, we go from 1 to n. And so this is the formula that I've come up with for the total overdue cost. And this is going to stand in some places in our math, in our proof, when we start talking about the cost of overdue books. Okay, we're going to compare one cost to the other, and we're going to need these sums to stand in there somewhere. So that's why I want to explore this a little bit beforehand, is to get to this sum. I don't want to be doing that when I'm writing my proof. Okay, and then let's just take a look here at the sum. The sum can actually be changed ever so slightly to change it around, but I think this is an acceptable one. It's basically saying that let's just plug in the values and make sure we did things right here. Okay, I'm telling you it's right, but I always double check to make sure. So if I plug in I equals 1, we get n minus I in this case is 1, n minus 1 plus 1, we get n. The first one will be n. If our n was 6, then that's right. What about the last one here? The last one we plug in is n. N minus n is 0, so we get +1. The last one is 1. Hey, that's right too. So after plugging them in, it looks like we've got our formula here correct, expressing the numbers that we want it to in the countdown here. So now we can use this. We can deploy this when we need to do a little bit of math in our proof. I've written a little bit of pseudocode here, but hopefully you can see that pseudocode is very basic, and it's really unnecessary. We don't really need to write pseudocode here to express this algorithm. And in fact, in greedy algorithms, almost always the greedy algorithm, at least for these kinds of simple problems like this, can be stated in a single sentence or a single phrase. And so here I've just got sort of a couple different ways we could express this algorithm using natural language instead of relying on pseudocode. Read the books in ascending order of length. That's one way to do it. Always read the shortest book first. That one's stated in the way of a greedy algorithm, because greedy algorithms think about making a local choice, and then that should lead to a global optimum. So our local choice is saying, well, what should I do right now? Just read the shortest book. And when you're done it, now what? Just read the shortest book again. Just keep reading the shortest book, and you will satisfy this algorithm. And then the last one is, again, just another way of restating this. Well, just read the books from the shortest to the longest, kind of merging these two together. Okay, all of these are acceptable statements of the algorithm, and if anyone asked you, hey, what algorithm should you use, all of these should be acceptable. I'm not focusing on runtime analysis here, usually because runtime analysis of these algorithms is so straightforward. You can either just leave it to the side or leave it as a single sentence comment, like sort of I've done here. Is we can see very clearly looking at this pseudocode here that what does this do? It does nothing. It sorts it. Okay. And so how long does that take? Well, n log n in the worst case using something like a merge sort. Okay. But what we're left at is, can we prove this algorithm is correct? Hopefully we can. It is correct, but let's see if we can prove it. All right. So again, to get started on our proof here, we need a theorem to prove. And usually the theorem is our algorithm is correct. But that's a very vague way to state it, and we don't want to have vague language, so we want to be a little bit more precise. So when we're talking about our algorithm, we want to state it in a way that is going to be simple and easy to state so that our reader can understand it. So here I've chosen the natural language version of always reading and returning the shortest book first will minimize the overdue cost. Now, maybe I should put total in there, but that the word total is not necessary, but it very much emphasizes that we mean the output, the final cost. Okay, again, this proof I'm going to do is going to be at a pretty high level. It's been edited multiple times, so it didn't flow out of my brain this way. And when I say multiple times, I mean a dozen times at least. So to make it as clean and concise and precise as it is. All right, so starting off, we want generality. Generality meaning not proof by example. We can't just say we have these books to read. We have to say assume we have any old set of books to read. So assume that the books that we have are any old books. And then what I'm going to do here is set them up so that they are in the order that we would read them in. Okay, so here I'm saying put them in the ordering shortest to longest and call that T. So in a weird way, we're almost assuming they've given them to us in the right order. But again, if they haven't, we know our algorithm would sort them and put them in this order. So we'll just call it T. This is the order that we want our books in. Now, like we did in our previous one, we want to consider any other ordering. But any other ordering is sort of awkward to choose here. So what I'm going to do is I'm going to say, imagine what we do is we're going to change this ordering into another ordering, but one that's very similar to this one. And how we can do that when we're talking about permutations is with swaps, where if you swap any two positions in a permutation, you'll get a new permutation. And often, if you only do one swap, we say that's we might say that this is one move away from another permutation, depending on how we're measuring how close permutations are. One swap meaning we can change it back with just one swap. That's kind of an interesting thing to consider, and that's how I'm going to proceed forward on my proof. So I don't have to consider all the other orderings. I'm just going to consider ones that we can get by doing a swap. Now, again, why is that going to be sufficient? Is because any other ordering that I can create by making swaps. So I just keep making enough swaps, and eventually I'll get to that other ordering. So we're just going to consider making one swap and see what that does. Okay, so say we've got our ordering of books T, and we're going to make a swap, and I'm going to swap positions I and J, and afterwards I'm going to call it T prime. Now, see this little bracketed bit here, such that I is less than J? That's the kind of thing that I put in afterwards in one of my edits. Okay, when I started writing this, I said, okay, let's just considering I'm swapping these two positions. I needed names for the positions, right? And so I and J made sense. And then I didn't realize until later on that somewhere down the road, it was important for me to know what the relationship between I and J was. And so later on, when I got to that point, I was like, oh, gee, I need to know what order they are. It doesn't matter up here what order they are, but down there it did. And so down there, I'd said I wanted I to be less than J, so I ran up here and I re-edited this line and put that in there. So let's hopefully when we get to that line below, I'm going to come back to it and say, hey, see, look, we needed that I less than J bit here, and that's why I put it in there. Okay, so again, this didn't flow out of my brain this way. It came through a bunch of edits and going back and forth. Okay, now what am I going to set up? I want to set up the cost of my two different orderings, cost of T and the cost of T prime. Okay, and I'm just using exactly those formulas we had on the previous slide. Okay, I think one thing I've done here is I've changed the I's to K's, which doesn't do anything to the formula, but it's because I already had an I here. I don't want to confuse anyone. Here I got K's, there I got I. Okay. And then what I want to do is I want to go ahead and do the same kind of comparison we've done in our previous example, which is now that we've got the cost of these two different, let's compare them by doing the difference of those costs. Remembering if that difference is equal to 0, that means they were the same. If that difference was greater than 0 or less than 0, it tells us which of the two was bigger. And that's ultimately what our goal is. So we've got this going on here. We've got this reading the textbooks in this order or reading the textbooks in the other order after the swap. Well, let's remember that just like in some of our previous proofs, most of these books are at the exact same position. So all these terms for the books that are in the same position are going to cancel out. You know, we might have 5 minus 5 or 10 minus 10 and so on. Those are all going to cancel out. But the only ones that are not going to cancel out are position I and J. So let's look at I and J. Okay, so that's what the next bit here. Since the only difference between T and T prime is that position I and J, all the other terms cancel out. So T minus T prime must be, let's make sure we're looking here. Out of this sum, I pulled out I and J. I, J, J. Out of this sum, I pulled out I and J. I, J, J. Okay, so those are the ones that didn't cancel out and I left them there. Okay, and now I'm just going to do another substitution. The next substitution I'm going to do is say, hey, remember that these are the same books. All we did was swap I and j. So t prime of j is equal to ti, and t prime of I is equal to tj. So in this second formula over here, I got rid of the t primes and replaced them with t's so that I can start factoring them out. The goal there is so that I can, now I have this term with a ti, I have this term with a ti, I might be able to factor them out and do some algebra that's going to help me here. So indeed, well, okay, that is the next thing I want to do, but I want to be careful with my minus. I'm just trying to be very careful in this next step with my minus that I don't forget minus this plus. So I've changed that plus to a minus, but I really here I'm just dropping my brackets and propagating that minus in. Now we're going to start factoring out. Okay, what can we factor out? We got some TIs, we got some TJs, so I'm going to factor out here. Oh, actually, I said I was going to factor out the TIs and the TJs. It looks like I'm going to factor out the n minus I minus plus 1s instead. So I'm speaking here as though I knew what I was going to do on the slide, but my instincts in my brain differed from my instincts in my brain, yesterday when I made these slides, and that's okay because if you did that other step, it will lead you to the right answer too. Okay, we got to factor one out and then we got to factor the other out. So here what I'm doing is I'm saying this term here has an n minus I plus 1. And this one has an n minus I plus 1. So I'm going to factor that out, and that gave me a ti minus, being very careful here, a tj. So I got ti minus tj here. Then we do the same thing with this one, n minus j plus 1, n minus j plus 1, factor it out. We get tj minus tj minus ti. Next thing we notice, look, this is ti minus tj, this is tj minus ti. These are actually the same value. It's just one is the negative of the other. Let's just test that out in our brain for a second. Say we had 7 and 2. 7 minus 2 is 5, right? But 2 minus 7 is minus 5. These are the same number, it's just one is the minus of the other. So what I'm going to do now is factor out a minus. Factor out a minus. So I'm taking the minus out of this one so that this minus, or this positive tj becomes a minus tj, and this minus ti becomes a positive ti, and I just swap their position because it's easier to, it looks nicer when we write it this way. And then that minus that I factored out popped out front here. Okay. Now what it means is this term is the same as this term, so we can factor it out. So we do. We factor it out, and we get now this n minus I plus 1 and n minus j plus 1. And luckily, a lot of the stuff in there is going to cancel out. Our two n's, our two 1's, and we're just going to get a minus I and a plus j. So we get j minus I. Okay, so I get here, and usually when I get to about this state, I'm like, this is looking pretty good because I probably am going to be able to know if this is a positive or negative number as long as I know something about j and I and ti and tj. Okay, now let's go and see. Now this is that point where I said, what do I know about j and I? And I went back to the top and I said, oh, I don't know anything about j and I. There could be any relationship between j and I. And I could finish the proof off down below here saying something like, well, if j is less than I, this happens, and if j is greater than I, this happens. But I don't want to do that. I'm just going to go up ahead and say, no, let's assume that I is less than j, so that when I get down here, I know I is less than j. So j minus I is what? Positive. So we might, sometimes I write, if I'm doing this on the board, I'll write a little positive, a plus above there and say, okay, this is plus. But what about this one? Let's see what we know about this one. Ti and tj. Okay, I don't know. I might have to go and think about t for a second here. But again, what do I know about I and j here? I already said I is less than j. Okay, so ti and tj where I is less than j. Well, what order is t in? Assume all the books are ordered from shortest to longest. Call this ordering T. So if they're ordered from shortest to longest, that means TJ, which comes later, must be longer than TI, which comes earlier. So this is the shorter, this is the longer, so this one must be a minus, a negative. And what happens when you take a plus and you multiply it by a minus? You get a minus. Okay, so this whole thing must be negative. That's all I'm arguing here. Hey, this one's greater than 0. A little subtlety that slipped out of my mouth. I said it wrong, even though luckily my slides got it right. I said this one must be a minus. There's the possibility they might be equal to each other too. Okay, we said they're in increasing order, but remember there's always the possibility of ties, so they could be equal. So I'm glad I was careful here. Okay, so we know this relationship is less than equal. Okay, not strictly less than, and so this is also less than equal. Okay, which means we've got a positive number multiplied by a negative number, or 0. It could be 0, in which case we could still get 0 here. And what that means is the difference here is less than or equal to 0. Okay, now is that good or bad? Let's remember, what were we looking at here? We've got a list of books. We're trying to minimize the overdue cost. Okay, and it's showing us here that T, the original one, that's ours, that's the good one, okay, is less than or equal to T prime. That was the alternative, the one we did when we did the swap. Okay, so what does this tell us? It tells us our cost is less than or equal to the cost of any other one we do after we make a swap. So what that means is no way we swap the books will decrease the cost of our ordering. Does that mean it's the unique only one? No, remember, if case of ties, we might have different ways to read the books, but it does mean that ours is guaranteed to give us the optimal solution, or the minimum overdue cost every time, which is great. Okay, again, I want to highlight that this proof was written, didn't come out this way. It was probably the 15th draft I've written of a proof of this particular algorithm, and that's because that's how proofs really work. Is you keep honing them, making them more precise, more concise, more correct, and cutting out more irrelevant information. But again, it doesn't flow out of me this way, so I want to sort of share with you sort of more of an intermediate stage proof that I may have written. So this is usually where I start before I get to something that looks like this. So here's my secondary attempt at this proof. Again, starting off a little bit more formally this time, strictly saying, hey, assume we have an arbitrary list of reading times. And then again, trying to set up our variables, with actual things to talk about. In this case, we're looking at, in the last one, I just said, hey, imagine we have this list T and so on. Here, I want to give them a strict name. So I'm going to say, let S be the list of books that we would come up with in the order of shortest to longest. That's our solution. Usually I use S for solution. And then O is going to be the optimal one. So usually I use O for optimal. It's going to be the list of books in an optimal order. We don't know what that order is, so we shouldn't say it. So for instance, we shouldn't say in order from shortest to longest. The only thing we should say is that it's optimal, meaning it has minimum overdue cost. Okay, of the total overdue cost, it's the minimum. Okay, again, what else do we know about it? Really nothing. Okay, if S and O are already the same, if they're in the same order, then we know S is optimal and we're done. So again, just like in our previous proof, here we just say, okay, we know this is an easy branch, but let's not look down that branch because it's the easy branch. Look at the other branch where they're not in the same order. Let's assume S and O are not in the same order. Okay, so here we need to do a little bit more setup. So let's see if we can follow through. Okay, so if S is not equal to O, we're going to start looking at the books one at a time. And we're going to start with the first book that S would read and the first book that O would read. And we're going to look at them one at a time, and we're going to see where they differ. Because if they're not equal to each other, there must be one of these books that is not different. Okay, so that's where I get to here. So if S is not equal to 0, there must be a first book where they read different books. So let's go and pick that out. Let's call that the ith book. And then we'll just call S, we'll say S reads SI, and we'll say O reads OI at the ith book. And those are different because we've assumed they're different. Okay. Then, since O must read all the books, both of them must read all the books, but since O must read all the books, we know that SI, the book that is read by S, must be read later on. Okay. Whereas OI is being read in its place right now. Okay. And let's assume that that book later on, since it's in O, it's probably got an index in O, and let's say that index is J, and we'll say that, OJ is the one that's equal to SI. Again, so far I'm really just labeling stuff, giving names to things because I want to talk about them. What do we know? Well, because that OJ is later on, some later point, that tells us that J is greater than I. Hey, that's the same property we just had in our last proof. That, again, remember these these same things are going to come up again. Okay. And why is that? Since I was the first book that was different between S and O. Remember, they agreed on all the books until we got to this one, so we know SI must appear later. Okay. What else do we also know is that because of the way the ordering that S puts the books in, which is from shortest to longest in the reading time, we know that SI must have a less than or equal to order or sort of reading time than OI, the book that O chooses to read. Okay, because remember, we read them from shortest to longest. If if our ordering S would read this book OI later, then that means it must have a larger reading time, or maybe the same. It could be equal, and that's something that's important for us to consider as well. Okay. Again, and that's because S reads the books from shortest to longest. Okay, so all of this is set up. Why is this all set up? It's because I wanted to get names for this book SI. I wanted to get a name for this book OI. And then I wanted to consider, what do I know about these books? And what do I know about I's and J's and so on? And get all that information set up. So I know J is greater than I, and I know this relationship between SI and OI must exist. Okay, so now, similar to what we've been trying to do before, and just like we did in that last proof, we're going to do a swap. We're going to swap. Now, we want to be careful here. Sometimes we think maybe I should change S. That's what I just did in the last book. In the last proof, I just took the optimal solution and said, what happens if we change it? It gets worse. In this one, we usually have an opposite strategy. Our opposite strategy is, let's change the optimal strategy, the optimal solution. Because if it gets better, then it was never optimal to begin with, and that's a contradiction, and we usually like that on this branch. Otherwise, if we change the optimal solution and it doesn't get better, it stays the same, then the new one that we've changed is still optimal, and we can repeat our proof with that one instead. Okay, so that's all I'm doing here is setting up this swap. I'm saying, imagine we're going to alter O, do a little surgery on O, cut out OJ. Sorry, don't cut them out because they're in an ordering. Just swap them, move the two positions, move I into position J and J into position I, and we'll just call this new solution O prime. Okay, now remember our properties of validity and optimality? Well, we just changed an optimal solution. It may no longer be valid, so we want to make sure it's still valid. What was the condition of validity in this problem? Was only that we read all the books in some order, any old order. So we notice that after the swap, we still read all the books. So that means we're still valid. Okay, but also the extra bit is now O prime agrees with us on book I, which is good. And so if it is still optimal, that's good. We haven't confirmed if it's still optimal yet. And so now what I'm saying is, like we've done before, let's try and compare the difference in cost between these two, O and O prime. So again, I'm going to give them names, CO and C of O prime. Again, trying to be as formal as possible, giving names and labels to things. So here I've got CO, that's the cost of CO using that formula we've used before. CO prime, same thing, only just swapping out the O for O prime. Let's continue our proof on the next slide here. And then we're going to go ahead and try and compute the difference in the costs. So this is the same, again, hopefully from that last proof, we're like, hey, gee, that looks kind of familiar. Before we maybe had T and T prime or something like that. It's just the names that have changed ever so slightly. And again, same as before, I've left out the sentence that that justifies this because it was on the previous proof, so hopefully we still remember it. But since most of these terms are the same, they cancel out, only the terms in position I and J don't cancel out. Okay, and so I've included those terms here. Maybe did a couple steps, moving that minus inside and so on. And then now we're just doing all of that factoring out. Well, let's factor out the n minus I. Let's factor out the n minus j. So we factor those out. Then we factor out that minus here, so we could switch these orders around and put the minus here. And again, let's factor that out. So we factor that term out, and now we have some little bit of algebra to do here. All this math is exactly the same. All this math for this problem is exactly the same. Every problem is going to have slightly different math, but all this math is exactly the same. So again, when we get to this bottom part, well, the same reasoning happened, because remember, out in the setup, we said, hey, J is greater than I. We said some relationship between these two as well. So those relationships happen to be the exact same relationships we had in our previous proof. So we're using the same propositions to justify the ends, which is probably good because the proof should follow from the same premises. Okay, so again, let's just follow through some of these points here. What do we know about j minus I? J is greater than I, so this must be positive. What do we know about OI and OJ? OI is greater than or equal to OJ, so this one must also be positive. Okay, it turns out, remember last time we had a positive and a negative? Well, this time we switched it around. The last time we were trying to say ours is better. This time we're trying to say the old one, the ours, is worse than this new one that we've come up with. And so that's what we've actually got here. It ends up that the cost of O, remember that was our optimal solution, is greater than or equal to the cost of O prime, which was our solution after we did surgery on O. Well, if it's greater than, then that means O was never optimal in the first place. And so that's my first one. If it's greater than, this is a contradiction. We assumed O was optimal, so we can't find another one that has a better total cost. And then also, so that's the first bit saying, hey, this is an impossible branch, so we can't go down it. So that means that these costs must be the same. And if the costs are the same, that means O prime is also optimal, but it also agrees with S on the ordering of books, at least up to this point. If it still differs, that should say S there. If O prime still differs from S, then we can repeat this argument until it agrees with S. And this is just a little post-amble, which finishes off the proof, tells our reader, hey, we're done. All right, that's it for my library books video. This is sort of the second problem we're looking at for greedy algorithms and greedy algorithm proofs. So I hope this helped you understand how you might prove a greedy algorithm correct. And again, stay tuned for the next video where we're looking at another algorithm. So thanks a lot for watching, and we'll see you in that next video.